All right, so now what we're going to do is we're going to kind of return to an idea that we've explored a little bit, just slightly in the past, and that is, suppose we have a curve and from a function, and we're restricting it to b from just a to b. We would like to find the area under the curve. So in other words, the area of this kind of oddly shaped surface, right? So you want to find this area, right? Okay. So we want to be able to find the area. Now we've done this in the past, right? So if you remember what we've done is we've filled this area. Let me do this real quick. All right, so I just made a copy so that I could write on this first one. What we've done in the past is this. We would take this and divide the interval between A and B into a certain number of segments, right? In this case, we've got 1, 2, 3, 4, 5, 6, 7, right? And then we would, using either the right hand, so we're using the right hand side of each segment, we'd go up until we hit the curve and then create a rectangle. Boom, right hand side, hit the curve, create a rectangle that tops out at that right hand rule. So this is the right hand rule. Okay. So we covered this area with rectangles, and we can find the area of each of those rectangles, add them up, and that gives us an approximation of the area that we want. And then we do it again with skinnier rectangles. So now we divide each of these in half, and now create rectangles that go up. So I'll exaggerate. That goes up there. This one goes up there. And so we have skinnier rectangles. Find the area of those that doubled number of skinny rectangles, add them up, and that gets us a better approximation to the area. So that's what we're going to do here. Okay, we've done that. We just keep doing that process and get better and better approximations. So we're going to do this, but we're going to lay the groundwork out in notation here a little bit and see how this works. So I want to find this area. So the first thing we do is we decide, okay, how many or how wide do we want our intervals to be? Okay, so the width is something that we'll call delta x, right? We want our rectangles to be delta x wide, and the way we figure that is we do b minus a divided by n, where n is how many rectangles, right? It's how many rectangles we're going to use to cover this. All right, so if we want to cover it within rectangles, then each of those rectangles is going to be b minus a over n wide. Okay, now what we're going to do, so let's just draw this in here a little bit. So here's our first rectangle, and we're going to use the right end rule. So we go up, and then we go over, right? And this distance is delta x, right? Each of these rectangles is delta x wide, which we remember is b minus a over n, okay? Now we're going to label these a little bit. So we've got our first rectangle, right? So we'll refer to this as the first rectangle, the second and the third, and then there would be more here, all right? Now let's also label these points. This point A is x sub 0, and then this is x sub 1, x sub 2, x sub 3, and so on. So x sub 1 is the right hand end point of the first rectangle. X sub 2 is the right end point of the second rectangle. Okay? And so we have a little formula for each of these. And so let's write it. X sub I, so the ith x, right? Because I need to know what numbers these already are. They're going to be x sub I, the ith right end point, is going to be x sub 0, which is A, right? This is A, plus I times n, or sorry, I times delta x. Okay, or x sub I is equal to A plus I delta x. Okay, so if I want to know exactly what the value is of any of these right endpoints, if I want the value of this, say the fifth endpoint, the right endpoint of the fifth rectangle, I would x sub 5, let's write it down here, x sub 5 would be A plus 5 of these delta x's that we've already calculated up here. Delta x is up here, okay? So again, we're just trying to develop the notation so that we can be flexible on this. All right, so if I want to then find the formula for this thing, all right, the area of these rectangles, so we'll call it the area, the blue area is A, okay, that's what we're after. That's going to be approximately what we're going to call the, we'll call it as the right endpoint, R sub n. So R sub n is the area of n rectangles using the right endpoint approximation. So if you look at this, it's going to be like this. The first rectangle, bam, this rectangle right here, its area is going to be its height, which is f of x sub 1 times delta x. All right? So this is the area of the first rectangle. Plus the area of the second rectangle, it would be f of x sub 2 times delta x, plus the area of the third rectangle, f of x sub 3 times delta x. And we keep adding up the areas of these rectangles until we get to the nth, or the last rectangle, f of x sub n times delta x. Okay? And looking at that a little closer, we notice, hey, I can factor a delta x out. And if you factor a delta x out, all you've got is f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub n, right? Or, more concisely, delta x times the sum of the f of x sub i's, right? That's kind of nice. So if you look at that, if I want to find this area of these n rectangles, all I need to know is how wide they're going to be, which is the first thing I do, right? Delta x. And then I just add up the value of the function at each of the x sub i's, or the value of the function there, the value of the function there, plus the value of the function there, plus the value of the function there, until the value of function there. So that would be the right endpoint rule. Okay? Now the left endpoint rule would be using the left ends. So let me just write down what that would look like. I need to add this real quick. This summation should go from I equals our first to our last. Okay. Now, if I use the left endpoint rule, I'm going to use L sub n. In other words, that's the area of the n left areas. It will look like this: f of x sub 0, right? Because you used the left endpoint, which is f of x sub 0 plus delta x, f of x sub 1 times delta x, all the way up to f of x sub n minus 1 delta times delta x, or delta x times the sum from I equals 0. Well, we can do it this way, actually. I equals 1 to n of f of x sub I minus 1 times delta x. So you're just adding up all the left-hand boundaries, and that's how you get the left-hand rule. All right? So this gives you an introduction to the process of using what are called Riemann sums. Okay, Riemann sums to find the area under a curve. Okay, we'll dig more into this in our next section. But I'll create one more video that shows you how to do this, and we'll actually work an example so that you have this process. You can see this process live and in action. So watch for that video to see an example of this.